Welcome back to ME 760 Engineering Analysis 1. So today's lecture will be a new topic in differential equations. It's not in the book. It will be the how to solve a coupled set of ordinary differential equations, first order linear differential equation coupled system. And we talked before that if you have nth order differential equation, you can decompose the nth order differential equation to a set of linearly coupled ordinary differential equation of the first order. So this will be the new topic for today's lecture. It will be this lecture. I want also to remind you, one of your friends, he reminded me last time that when I wrote the Wronxian for the solution for the solving the particular integral, the last method, I equate the matrix to zero, Wronxian to zero, and this was not true because you need linearly independent solution u1 multiplied by y1 plus v1 multiplied by, or u multiplied by y1 plus v multiplied by y2 equals to 0. When u and v both are equal to 0, this means that they are linearly independent. So if you need linearly independent, definitely you need the vector vu should be equal to 0 and the Wronxian should not be equal to 0. Otherwise you will not be able to invert the solution and get the 1 over Wronxian. So let's start the new topic, today's topic, and it is coupled ordinary differential equations. And again, this topic is not in text. Usually, we used to have y of x, but excuse me, for solving the system of linear differential equation first order, usually we'll encounter those as time variation, stuff like dy by dt. So from now on in this lecture, we'll just consider y of x as y of t, and instead of just the independent variable bx, it will be time, for example. So the general form for the coupled ODEs is y1 prime is just equal to f1 of time t y1 up to yn, and y2 prime is just another function f2 of t y1 again up to yn. Again you will have this up to yn prime, and it is equal to fn of t y1 and again up to yn. So if we assume that our system here is linear, what do we mean by linear system?
You can make up one with the linear combination of the others.
No, I'm talking about linear system, linear differential equation. I'm not talking about the solution being linearly independent solutions. So linear system means none of your dependent variables has any degree greater than 1. So 0 or 1. So in this case, the functions f1, f2 up to fn, we call them fi of t and y1 up to yn, can be written as ai1 y1 plus ai2. I means subscript for f1, f2, f3, and so on. So ai1, y1, ai2, y2 up to ain, yn plus gi of t. So this is just, if you remember, this is just the definition of what? The definition of linear order differential equation was constant what? Constant what? Constant coefficient. So just the the definition here. But this is, of course, will be if I will be equal to what? y1 prime, so this is just a first order differential equation. It's not nth order differential equation, but the same methodology. We transformed a couple of lectures ago when we studied the differential equation at the very early beginning, that we can transform a system of n, an nth order differential equation to a system of n first order differential equation linearly coupled. Okay, guys? So usually the solution for this equation, y prime of t, if we write it in a matrix form, so now we will return back to our matrices. So I put here the this vector notation. This means that y is in a vector form, y1, y2, y3, y4, and so on. And the coefficients here, the matrix here will be what? The matrix A. So maybe the coefficients here are constant or function of time t. So it might be a linear differential equation of the first order with constant coefficient or with variable coefficient. So I will put 2 over A here, meaning that this is a matrix multiplied by the vector y plus the other vector j of t, which means that this is a vector of all the inhomogeneous term on the equation. So we will solve this with the initial condition that y of t equal to certain vector k naught. So again, how to solve this system of equation? So we will try to look at the solution. So we have 2 solutions. One, we will solve the homogeneous equation, and then we will try to find the solution for the particular integral or the inhomogeneous equation. So let's try to start and seek the solution for the homogeneous part. So homogeneous linear system with constant coefficients. So we'll consider the system as y prime of t equal to a multiplied by y prime of t. Again, this is a vector, this is a matrix, this is a vector. So if somebody asks the hats that we put on the top of each one of those. So usually we will seek solution in the form of what? For solving linear differential equation with constant coefficient, what was the solution? Exponential functions. So we will seek the same solution. We will seek a vector y equal to a vector x e to the power of lambda t, where this vector x here is the vector, let's say, a vector of either constants or, let's say, constants multiplied by e to the power of lambda t. Okay, so this is the vector here. The vector y will be the vector x, and you can take e to the power of lambda t outside. So if you substitute with this in this equation, what you will get is y prime will be what? Lambda multiplied by the vector x e to the power of lambda t equal to a multiplied by x e to the power of lambda t. E to the power of lambda t will go with e to the power of lambda t, and you will have ax equal to lambda x. So what's this?
Eigen Vectors.
This is Eigenvalue problem. Yes? Eigenvalue problem that we have been studying for quite often during this semester. So you transform it a system of linear first order differential equation to an eigenvalue problem. So x here will be the eigenvectors, and lambda here will be the eigen what? Eigenvalues. And what are the lambdas? Lambda are the characteristic equation solution of your equations. Yes? So lambda are the eigen values of matrix the matrix A it is the solution for characteristic equation determinant of A minus lambda I equal to 0. And how many lambdas do you expect? N lambdas. Call it lambda sub I. And what are the x? So lambda sub I is the vector, the individual elements of the vector lambda, and x sub I is the individual vector value for the vector x. So xi are the eigenvectors associated with lambda I. So the most general solution will be just the vector y of t will be the summation of what? Ci xi e to the power of lambda I t. Yes? Okay guys, do you have any questions so far? What if, this is if we have distinct eigenvalues. So we'll have this solution, yes? So this is for what? For distinct eigenvalues. What if we have degenerate eigenvalues? Degenerate eigenvalues. So it is exactly the same. What did we do when we have multiple roots? What we did? We seek another solution because you will have multiple y. Let's say that you have lambda from the characteristic equation, lambda equal to 1 3 times, repeated 3 times. So you will have y1, y2, y3. They are the same. Yes. Let's say lambda equal to 1, so it will be e to the power of what? 1x, e to the power of 1x, e to the power of 1x, or e to the power of 1t, e to the power of t, e to the power of t. They are not linearly independent, so we have to seek another solution, and we reach to the conclusion that we will have what? E to the power of t, t e to the power of t, and t squared e to the power of what? T. So this is similar to the same manipulation that we try to do. So we will suppose that the determinant of A minus lambda I is equal to lambda minus lambda 1 all square multiplied by some h of lambda. H of lambda is just the rest of lambda, so it will be lambda minus lambda 2 multiplied by lambda minus lambda 3 multiplied by lambda minus lambda 4 up to lambda minus lambda n. So this is just the h of lambda is exactly like last time from I equal to what? 3 to n lambda minus lambda I. So this is exactly the same like last time. And how many roots we have right now? Two roots are repeated roots. So we have two degenerate eigen vectors. So the solution will be y prime equal to y multiplied by a. This is one solution, only one solution. You remember last time we have one solution is e to the power of what? E to the power of t, and the other two solution will be what? Or the other solution will be what? T e to the power of t. So this is one solution. Then the other solution, but another independent solution we will seek in the form to be y2, so this is y1. So this is the general formula. The solution will be, one solution will be y1 equal to x1 e to the power of lambda t. So again, x here is what? Yeah, but it is the Eigen vector, but it's what? It's a vector of constant. It does not have the what? The independent variable t. Yes? So the other one we will seek it in the form of what? What do you expect? y2 will be x1t e to the power of lambda 1 t. And this should be lambda 1 here, plus some u e to the power of lambda 1 t. So the only difference between the case of a linear differential equation, coupled linear differential equation, a system of linear differential equation, is we introduce some u e to the power of lambda t. Okay, guys? So if you look at only the solving an nth order differential equation, for example, and you have repeated root, it repeats twice. So the first one will be e to the power of, let's say, e to the power of lambda 1t. The second one will be what? T e to the power of lambda 1t. Yes. So here is this one, t e to the power of lambda 1t, and this is the vector, eigenvector for the constants or whatever, and this is another term here that we added u e to the power of lambda 1t. So how we will find u? What do you think? How we will find u? Huh?
Special conditions.
Nope. So this is a solution of the equation. So all what you will do is what?
Plug it back in.
Huh?
You just plug it back in.
Yeah, plug it back in. Try to seek this solution. So let's call this is 2, and this is the differential equation here, 1. So all what you will do is just substitute 2 and 1. So when you substitute 2 and 1, you have y2. You have to differentiate it because this is y2 here. When you substitute, you need the y prime, so differentiate it. So this will give you y2 prime as a vector is equal to x1 e to the power of lambda 1t plus lambda 1 x1 t e to the power of lambda 1 t plus lambda 1 u e to the power of lambda 1 t. Okay, guys? But this is the left hand side. This is y2 prime. Right hand side is a multiplied by y. Yes? A multiplied by y2. So what's a multiplied by y2? So it will be a multiplied by what? x1 t e to the power of lambda 1 t plus a u e to the power of lambda 1 t. So what's a x1? This is the eigenvalue problem. So ax is what? Lambda x1. So we have to equate those two terms. So when you equate those two terms, you will end up with x1 e to the power of lambda 1 t plus lambda 1 x1 t e to the power of lambda 1 t plus lambda 1 u e to the power of lambda 1 t equal to lambda 1 x1 t e to the power of lambda 1 t plus a u e to the power of lambda 1 t. So this term here first of all we'll cancel e to the power of lambda 1 t from all sides. Then we have what? Lambda 1 x1 t and lambda 1 x1 t will cancel out. Then when you write it down, this will give you x1 plus lambda 1 u equal to a u. Or if you rearrange it, this will give you a minus lambda I u equal to x1. But we have the condition for our solution was a minus lambda I equal to what? Equal to 0. Yeah. Yes, this is the eigenvalue problem, you want to solve it. So we can still solve for what? For you. So I will give you an example so that it will be clear for you guys how we will implement this method. So example here. If we have the vector y prime equal to 4, 1, minus 1, 2, and it is only y1, y2. So this is just two equations, a system of two equations. Okay? Y prime equal to 4y1 plus y2 and y prime equal to minus y1 plus 2y2. So we will find the eigen what? Eigenvalues, which is lambda I. How we will determine this? So this is the determinant of what? 4 minus equal to 0, and this will be what? 4 minus what? Lambda minus 1 and 2 minus lambda. If you solve this, you will reach to lambda minus 3 all square equal to 0, or lambda 1 equal to lambda 2 equal to what?
3.
3. So you have what? You have degenerate eigenvalues. If you try to get the Eigen Vectors associated with this one, so x1 will be just 1 and minus 1 transpose, or 1 and minus 1. Okay, guys? So now we need to find u. To find u, it is a minus lambda 1 I u equal to what? x1. And what's this value here? A minus lambda 1 I. So 3, 4 minus 3 is what? 1, 1, minus 1, and this is what? Minus 1. u1, u2 equal to 1 and minus 1. This will give you what? u1 minus u2 equal to 1, or minus u1 minus u2 equal to minus u1. So it is same equation. So we have infinitely many what? Solution. Yes? It depends on the value that you will pick up for u1. u2 will depend accordingly on u2. They are linearly dependent.
Should u2 on your first equation be positive?
U what?
u2 on your first equation, you have u1 plus.
u1 plus u2.
Yeah, there we go.
Thank you. Okay. So just put u1 as 1, and this will give you u2 is 0, so your vector u would be just 1 and 0. And what will be your solution? We have the first solution is what? y1. Yes? And what's the second solution? Yes? So C1. What's Y1?
X.
It's X e to the power of what?
Lambda 2.
Lambda t. So what's X?
1 minus 1.
1 minus 1 e to the power of lambda is what? 3t plus C2. What's Y2? Y2 is xt e to the power of what?
Lambda 2.
Lambda t. Yes? Plus u e to the power of lambda t. Yes? So x is what? 1 minus 1 t e to the power of lambda t plus u. U is what? 1 and 0 e to the power of lambda t. Did you get it? Did you get it, guys? So it is exactly the same. It is exactly the same like solving the differential equation, but we are here solving a system. So we have, if we have a repeated roots, we will have e to the power of what? E to the power of lambda t. Yes. Plus t e to the power of lambda t. Yes. But we added a term here. It's called what? U of t. So now, what's left? We solved the homogeneous equation for the two situations, one with distinct eigenvalues and the other one was what? With degenerate eigenvalues. So it is exactly the same like before. To solve for distinct values of the characteristic roots, the roots of the characteristic equation, yes, and then we solve it for the situation where you have multiple roots. Then we have to solve for what? A particular integral, or solving the inhomogeneous equation solution. So the inhomogeneous equation will be just y prime equal to a y plus some function g of t, for example. So we'll call this 1. Your solution will be what? Y of t will be the solution for the homogeneous equation plus the particular integral as a function of t. So what's the first method we utilize to get the particular integral or particular solution? Undetermined coefficients, and this is for constant coefficients. So Aij are constant. Again, last time we stated that what? If you have your j of t in the form of what? Power of t, or e to the power of alpha t, or cosine omega t, or sine omega t, or sinh omega t, or cos omega t, any of those forms, you will pick up your particular integral to be the same form with a constant. Then you will substitute and get the what? The undetermined coefficients. So this was the solution. So it is exactly the same. So to give an example, if you have your G now as a matrix, it will be t cubed plus t e to the power of t over 7, and t2 is t squared e to the power of 9. So your solution y particular will be just same form. So you will assume a t cubed plus bt squared plus ct plus d. So a power solution. This is a power solution. You have to include all the terms for the power solution from the highest up to the constant. Okay, guys? And this will be multiplied by what? T over 7. And the other one will be what? E t squared plus f t plus g or h multiplied by e to t over 9. Okay, guys? Do you have any questions so far here? Any question? Just you will pick up, if this is power, you will pick up power, but you have in order to pick up power, you have to pick up power what? You have to take all the polynomial form from the highest order up to the lowest, and then you determine the coefficients. Okay, guys? So now, what's the other way of solving this? Method of what? Variation. Variation of what? And we already discussed the method of variation of parameter before the end of the last lecture. And we solved it only for second order differential equation where we have two only solutions. Yes? So now we will generalize it to get the nth solution. So let's assume that we will seek a yp equal to y1 of t, y1 plus y2 of t multiplied by y2 plus up to un of t multiplied by yn of t. Then what we did last time, we transformed this to a matrix. Yes, a matrix form. So this will be equal to y1 1 up to y1 n and yn1 up to yn, and this will be multiplied by, in a matrix form, u1 of t, u2 of t up to un of t. And again, I can write this. This is a matrix Y capital, and this is a matrix U. So we will take this and substitute in the equation 1. Here is equation 1. So we'll call this 2, and we will substitute from 2 to equation 1. So once you substitute it, you will have what? You will have y prime u plus y u prime, and this is equal to a y u plus j, and we'll call it number 3, equation number 3. But all of us know that y capital prime is just equal to a y. From where this? This is what matrix? The matrix of solution. So it is the solution of what? y1, y2, y3 are the solution of what? What type of differential equation? If you look at equation number 1, the equation beneath it, how many terms here in the solution? Homogeneous term and particular term. So this is the solution of what term? Homogeneous term. Yes? No. This y1 and y2 and y3. So when we solved it before, our solution was what? Y equal to summation, for the normal case, summation of ci yi plus y particular. Yes? This is just for the solving differential equation without a system of differential equation. Yes? So we have y1, y2, y3. If we have third order, y up to y3. If we have fourth order, up to y4. If we have nth order, up to yn. So those are also the solution for what? For the homogeneous, and we are seeking the solution for the what? For the particular. So this is the particular. We propose the particular to be u1 multiplied by what? y1. What's y1 and y2 and y3 and yn? Solutions of the homogeneous equation, but we multiplied them by a function called u1 U2, U3, U4. So we end up forming a matrix Y, and this matrix Y contain the homogeneous solution of the equation. Yes? So when you substitute with this matrix, you knew that Y prime equal to A Y, and this is what? This is just if you substitute with Y prime equal to A Y, this is the homogeneous solution. Yes? So we can cancel the term what? A Y was what? Was Y prime. So we can cancel this term and what? And this term. Because this is Y prime operated over what? U. And this is A Y operated over A what? U. So if you operate this over U, operate this over U, you will cancel this term with what? With this term. So our equation will become so I have to, let me write it down here, Y prime equal to A Y Y, and this is since Yi are solutions of Y prime equal to A Y. This is the homogeneous equation. So 3 will become A Y U prime U plus Y U prime equal to A Y U plus G, and this Y U prime will just be equal to G because you will cancel those two together, and this will give you U prime equal to Y minus 1 multiplied by G, and we'll call this 4. So by getting rid of this term, we got an equation that we invert the Y minus 1, and we will got those equations that we seek to substitute here in the solution. So the vector that contain Y1, Y2, Y3, and Y4, and so on. So here is the, of course, this is not the vector that contain Y1, U1, U2, U3, U4, but this is what? It's derivative. So you can integrate back and get Y1, Y2, Y3, Y4, and so on. So somebody would say, do you think that there is a solution? The solution exists for this one or not? I would say what? Y minus 1 should have what? Y should have what? A determinant not equal to what? 0 in order to get Y minus 1 has a value. So the determinant of Y does not equal 0. Why?
Y has to be inverted.
No, but Y, it is indeed does not equal to 0. Why? Look at the equation over there.
Otherwise it'd be
What are the Y's? What are the components of this equation?
the solutions to the
Solution for the homogeneous equation, and the solution for the homogeneous equation should be linearly independent. So if you have a linear independent matrix, the vectors of the matrix form a linear independent set. The determinant of the matrix does not equal to what? 0. So the determinant does not equal to 0 since Yi, the vectors are linearly independent. So you will integrate equation number 4, and then you will get what? So you will integrating 4 will give you the vector u of t is just equal to y minus 1 j dt, and the particular solution will be what? Will be just this. So this will be this. Okay, guys, do you have any questions so far? The last method, I will just start it, then I will continue next time. It's called method of diagonalization. And in this method, your solution again, y for this equation the idea here, I will discuss this method next time. The idea here is to use a similarity transformation with certain matrix X. We will find this matrix X, so that when you use the similarity transformation, what's the similarity transformation? Minus 1 a x. This will give you what? A diagonal matrix that has what? So what did you do now? You transformed your matrix A to a diagonal matrix, and then you decouple your system of differential equation, because you will have just what? Lambda 1 here, and you will have y1 equal to blah 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 multiplied by lambda 1, and you can solve those independently from each other and get the final solution. So I will show you how the method will work next time. Do you have any questions so far? Okay, guys, see you next time.